Okay. Well, yes, I would also like to thank you for coming in on a Saturday as well. It's a beautiful day out there. Let's keep this light. Let's keep this interesting. Let's not get too technical today. I spend too much of my day talking about technology, math, software. By day, I actually work on Apache Spark as a committer, so I may have run into some of you on the mailing list. And today, I'd like to step back and talk a little more about history. I think this is maybe a more fun thing to think about when we talk about data science. So I'm from Cloudera. I'm Cloudera's Director of Data Science. I'm based here in London as well. And I got a couple people asking me what Cloudera is. Just for the record, Cloudera it provides distribution of Hadoop and its related technologies. So it's a data platform. It's where data lives. And not surprisingly, increasingly, it's a place people want to do their data science. So we are here for all your data science needs as well. But I won't pitch Cloudera today at all. I want to talk about history, and particularly the last 50 years of data science. And I've chosen the title because it's the title of a paper I really liked reading, and so I'm going to talk to you about this paper. And the paper is actually about another paper, which you should also read. So this is actually going to be a talk about lots of other talks and papers. And to save you time at the end, if you want to photograph this or copy this down, this is a short link to a list of all the pictures, all the papers, all the references in the slide deck today. They're all worthwhile. They're all nice reading for a sunny day in the park after this. So feel free to copy that down. This will be online later too. You can find this talk online if you're interested in following up and reading these papers I mentioned to you. Now, I get this question all the time. What is data science? It's kind of troubling that we keep talking about it. We have festivals about it, and no one can totally agree what it means. And we've all seen the Venn diagrams, and I'll have a Venn diagram for you later. But I almost wonder if this is the right question. Who cares what it is? Why don't we talk about what problem we're trying to solve? What is it we need to figure out when we say, what is data science? And maybe it's more useful to talk specifically about how we should teach data science. Or when we come to learn data science, what is it we should be learning? When we hire data scientists, what is it they do? What skills do we need to get work done in the field of data science? So that is, I think, the central point of the talk today. It's going to examine a paper that has an opinion, and I'll offer some other opinions about the answers to these questions. What is it data scientists do? What should they do? What should they know? As I say, this is a paper about a paper. A talk about a paper about a paper. The paper is this paper, The Future of Data Analysis. And if you know the history of the space, you may know John Tukey, you may know even this paper. So this paper was published, about 50 years ago. It was more like 50 years when the other paper was brought out. But more than 50 years ago, John Tukey wrote some thoughts about the future of data analysis. So it was his thoughts on how the field was changing over 50 years ago. Some of it was pretty interesting. It's a good read. It's about 60 pages. But this line at the end jumped out at me as quite prescient. He said, we need to face up to more realistic problems. Normal theory may offer a nice framework when the problem can be tackled simply or algebraically, but it can't be the stopping point. We can't stop at easy solutions to idealized problems. We have to, as a field, expect to take on more realistic problems and expect future generations to tackle even more realistic problems than they are themselves. So if you go back and read the rest of the paper, you'll see it's mostly arguing against a very theoretical approach to statistics being taught by the world of statistics and statistics departments. It very much started with assume idealized Gaussian noise, assuming very, very simple, elegant models and figuring out what you could prove from there. When, of course, people in the field practicing statistics knew that the world was anything but. Simplifying assumptions often were nowhere near true. And all this theory just wasn't necessarily helping people solve realistic problems. And so he cried foul and said, we have to deal with the fact that the world is not as we wish it were as academics. And we have to figure out how to stay relevant to the world of problems people are actually solving. So he does actually go on to mention the computer at the very end of the paper. He gets it about half right. How important is the computer going to be to the future of data analysis and statistics? Important but not vital is the interesting quote here. Okay, maybe. Half ain't bad, right? But at least he is already nodding to the idea that computing is going to somehow be the future of data analysis, not just figuring out theoretically what the solution to a problem is, but doing so analytically, iteratively, programmatically, on real data stored digitally. And I think, of course, that was correct. The whole story, almost all of the story of development of data analysis in the last 50 years even has been the story of data analysis as driven by computing. So we come to today, or at least the last 5 years, and we hear a lot of talk all of a sudden about data science. And what is data science? It seems to be this combination of big data and statistics, but I see a lot of the conversation dominated by the big data side of things, by the computing side of things. And I sense that people in statistics and applied math think this has happened. Big data has really come and drunk their milkshake. Suddenly, big data is a big thing, and the statisticians are wondering what the heck happened. All of a sudden, software engineers, like me, I'm a software engineer by trade with a CS degree and an MBA of all things. Suddenly, I'm a data scientist, and people are discovering anew things like like decision forests or neural networks. And these are, in a way, old news to this field, and yet suddenly it's the hottest thing ever. So something happened here. And I think it's useful to understand how the paths diverged in this field and suddenly have collided again, and what we can learn about how to go forward today. So I promised a Venn diagram. Here's a Venn diagram. It's a four-way Venn diagram. Again, data science seems to be defined as this conjunction of a bunch of different things. It's statistics, yes, but not just statistics. Statistics is just one piece here. It's one bluish piece of this complicated Venn diagram puzzle here. It also, data science is about communication, programming and hacking, and maybe business acumen and domain knowledge. And you have to have all four to be this thing that is the data scientist. Now, maybe all this is true. Maybe this is overstating it. Maybe this just reflects confusion. People seem to maybe define it this way because everyone actually views it slightly differently, and we're not all quite talking about the same thing. Maybe it's another instance of the light wave duality. We're both right. Yes, data scientists or engineers. Yes, data scientists or statisticians. We're both right at the same time. They're both at once, and they're maybe not even different things. It's just two aspects of the same underlying reality. So without a doubt, this is true somehow. We know that data science is part math, part engineering. But exactly what is real and what is hype? What is confusion and what's going to be a durable definition of data science? So this brings me back to the paper this is about, the paper about that paper. It's called 50 Years of Data Science, and it was published actually almost a year and a half ago by David Donoho from MIT. This is a great paper. This is worth reading. This link, as I say, is in that list of links I published at the outset there. This is worth reading. It is a rebuttal, I think, from a statistician to the big data movement. And it's a valid critique. You could take issue with some of the criticisms, but it is well argued, I think. And what I'd like to do is walk through some of the key criticisms he offers for the big data definition of data science. I think he wants to take back the term. He wants to reclaim the title from the engineers for statisticians, the mantle of data scientists, or at least admit that statistics is a really big part of it, and it's not all just another library you learn in your CS classes. So if you flip through the paper, section 2 is the fun section where he makes some claims, I will say. The claim, I'll paraphrase his section 2.1. Data science can't just be statistics on lots of data, because statisticians have always dealt with lots of data. And maybe that's true. I don't think there's been a time in history when people haven't wanted to scale a little bit more, when they've wanted to fit a little more data on the computer or to run that computation a little bit faster. And he gives the example of the US Census in the 50s. This was tabulated by punch cards, I think, for the first time. It was summed and aggregated on a mainframe. And of course, it was statisticians that did this work. So he likes to point out that it was really the field of statistics that was active at the forefront, at least in the 50s, of developing computational frameworks for applied statistics. And that's true, but in a way this, I think, only serves to underscore the point that even back then the future of statistics was applied. It was applying computation to the problem, not the field of statistics itself. And it actually took some engineering to scale up the ideas of statistics to apply them to an actually realistically large data set, the US Census. So in a way it's a fair point, but I think it almost underscores the opposite point, that it has been software engineering that has made statistics really relevant over the past 50 years or so. But a good point. The next claim, well, data science's contribution to statistics, whatever it is that's not statistics, can't just be the use of distributed cluster computing technologies because they are just so hard to use. Now, if you're older like me and you've been around the Hadoop ecosystem for a while, maybe you even once upon a time wrote some MapReduce code. And MapReduce is the original computation framework that put big data on the map, I would say, open source big data. And indeed, it was like the assembly language of big data. So he actually, in the book, quotes from the book that my colleague Tom White wrote about Hadoop and shows just how much code it took in MapReduce to compute the maximum of a huge set of integers. We've got a mapper that parses a line and parses an integer and then outputs it, then reduces it. Yeah, it's a lot of boilerplate code. And of course, in MATLAB or Octave or R, it's pretty much a one-liner. It's here's a max function, right? And he says, this is ridiculous. How can this be innovation? How can you get any meaningful work done if it's so hard to even do something simple like that? Well, in a way, not a great example because this was chosen exactly to maximize the exposition of the boilerplate. And the point is that there's not much actually going on here, and that it's just showing off all the structure that has to go around a very simple task. I'm not sure anyone says that that is a great way to compute a maximum. Of course, if you're using Spark, if you've been around the Hadoop ecosystem for the past couple of years, it's now also basically a one-liner in Spark as well. So this goes away and is replaced by that as well. I think it also fails to address the central objection people like I would have to saying, can't you just do this in MATLAB? Of course you can. Of course you can do this in R. Of course you can do this in Python. It's just that it won't necessarily scale. For example, good luck to you, taking 100 terabytes of data and finding the maximum of it that way in MATLAB. Good luck with 100 megabytes of it. Or good luck doing it over 100 megabytes if the 100 megabytes is not even on your machine yet and you've got to wait to copy it over the network. So there really still is something to the idea of easy scale, even if sometimes it's a little more complex. So I don't know if this is the best criticism to level at big data, not least of which because by the time you wrote the paper, this problem had gone away. Next claim. So if data science as a job, as a role, is just statistics plus some specific technical skills in particular packages, and those packages change every year, then, well, it's only statistics that is eternal. The math doesn't change even if this year we're using Spark and next year someone decides to use Clipper or Flink, and surely those aren't the important things to learn. Surely that's not what we should be teaching people. Surely we should be teaching them the stats, because the central limit theorem will always be true even if people one day stop using R, for example. That's true, but I think it probably overlooks the fact that you have to do your work in some language and in some environment. And these things are not necessarily unrelated. The languages and the tooling enable new applications of the ideas. And without those tools, we're back to Tukey's original problem of being far too theoretical and not applied enough. So I don't know if the idea that we should focus just on the statistics or primarily on the statistics is any more valid than saying we should focus on the tooling because the statistics are boring detail. I think they're both equally important. And maybe to support of that, I think a lot of people refer to this chart from the Banco and Brill paper a long time ago. A point this and maybe the unreasonable effectiveness of data we're trying to make is that, well, often simply having more data is the best thing you can do to improve your model. It's not better math. It's not more valid or fine-grained assumptions about the distribution of your inputs or the nature of the covariances. Sometimes just throwing more training data at a problem, whether more rows or columns, sometimes that's the best thing you can do. And simple machinery plus a lot of data at scale can give great results. If that's true, then maybe the key to improving the results of statistical models, of data science models, is at least as much advancing theory as is advancing the engineering and the scale and the data prep and the availability of lots and large data sets and lots of it. And in a way, I think the whole deep learning, the craze for deep learning these days further underscores this point. Deep learning is essentially simple ideas blown up to a ridiculous scale. And that turns out to be a really useful thing to do. Learning huge models over large data sets is great. It's made great strides. Now, at this point in the paper, he backs up and reviews history. How did we get here? From the 1960s, from the first paper, what happened? How did we diverge and then come back together here? What were the developments that led to this thing called data science that was no longer what we're teaching as statistics? And I'd like to highlight a couple milestones or waypoints along the way that he does, because I think they are, in fact, really important. Number one is the S language. So the S language was developed in the 70s at Bell Labs. And it may or may not be familiar to you, but you'll probably know its successor, which is R, of course, which is, of course, a very widely used statistical language. And if you're using R today, which is the successor to S, you're probably using something like RStudio. And this is not new to you. Even if you're using other languages like Python and Scikit in a notebook, this way of working is not new, where you've got code, data, and visualizations all together, sometimes even intermixed. So although it doesn't show it here, in R scripts, you can even write comments and documentation in comments in the code and have that, the code, the write-up and the documentation, and the data and the output all render together as one unit. And that's still a powerful paradigm. That was not necessarily something that existed before the advent of languages like S. S was one of the first languages that let you compute data or put data and analysis of the data together in one portable package that could be shared and run. So that shifted the paradigm somewhat away from writing theoretical papers and maybe sharing data some other way to being able to share a runnable, computable version of your analysis in a portable way. And that's a powerful paradigm, but it was enabled by software and technology. This pulled some of the center of gravity towards computers, towards environments that could run things like S and then R and so on. This pulled the field towards the notion of computing as statistics rather than just papers. So an interesting milestone. Another interesting paper he points to, an important paper, was the statistical modeling paper, the Two Cultures paper from Leo Breiman. So you may know Leo Breiman more famously as the person, the father, if you will, of decision forests. So his paper was the one that introduced decision forests about the same time. But this paper was about something else. It was about the culture, at least the two factions in the culture of the statistical modeling departments he saw, two different ways of thinking he saw emerging in the field. And one he called the generative modeling culture. And this culture was focused on questions of modeling the process that produced data, explaining why this particular data gave this particular output, trying to actually model the inside of the black box process that was occurring in the world, so to better understand what the real world process that was occurring. And he noted there was a different focus from another group of people, which he labels the predictive modeling culture, that it was not so concerned with how the black box was working, but was more strictly concerned with whether the black box's prediction or outputs were predictable, whether they were knowable. So not so much what's going on in the box, but can we predict, can we emulate this black box? And at the time, he suggested that 98% of the field was focused on this generative modeling culture, and maybe only 2% on this predictive modeling culture. But I would dare say that most people who have taken an introductory machine learning class, maybe on Coursera, are very much focused on the latter. The way it's presented and thought of in what we call machine learning is very much obsessed with accuracy, validation, producing a black box of some kind that is accurate at predicting image labels or detecting anomalies and so on. So somehow this bit was so useful that it won out, even though it was according to Leo Breiman, very much a minority view and a minority focus within the field of statistics, even as recently as 2001. In the same vein, he points to another paper, more recent paper, about the so-called common task method. And in a way, it's not a new idea as much as a description of an idea that is by now very familiar to all of us. It follows on this predictive modeling culture point from Breiman. So in a way, it's an attempt to explain why that culture took over. And I think the central point was that when you focus the problem not so much on describing the world, but focus much more on a much more objectively measurable outcome like accuracy, you drive innovation faster. So in this paper actually describes the progress of the natural language processing field throughout the 80s. He describes it as a field that made little progress at the time. He describes it as a field beset by, I think, what he calls glamour and deceit. He found a lot of researchers obsessed with obtaining interesting or beautiful models of language, not necessarily models that helped you predict how language worked or helped you parse speech or to extract things like entities from a sentence. And yet when the focus shifted a little bit and people started to focus more on black boxes rather than what was in the black boxes and focus on the accuracy of tasks like statistical machine translation, suddenly the field really made strides forward. Once people focused just on this outcome, it led to models that, as a side effect, did help maybe understand how language worked. But it wasn't because we were looking for it. It's because we were focused on this common task, predicting the translation of text with some degree of accuracy, and focused everyone on optimizing that number. That actually was a more productive way to move forward. And we see that reflected in things like Kaggle today. This is all of what Kaggle is about. If you participate in Kaggle competitions, it's literally the only view of machine learning that's on offer. Machine learning is about taking a known data set and optimizing its accuracy against some held out test data set. How you do it, what language, how fast it runs doesn't really matter that much. This is the common task method taken to the extreme. And in a way, Kaggle also is a demonstration of its efficiency. People from all over the world have spent literally decades of time optimizing for free, optimizing for the best possible model for a problem. And boy, they have achieved some really interesting results. So again, in a way, this was another step away from concern with theory. Why is the data this way? What does it mean about the world? Towards a much more quantitative, computationally driven field, where the concern was how can we get this to run faster, bigger, better to optimize for this number? And I think we then arrive in 2008, 2009. Hadoop comes along, open source, big data becomes a thing. And suddenly you find that these two fields have diverged. And we've got a huge culture that's built up a practice and tools around open source software, Python, R, et cetera, and now big data tools, and it's not the same thing that's happening in the world of statistics. And yet somehow all the focus is on the engineering, all the tools, the big data, and not the statistics. And maybe that's gotten out of whack. I tend to agree, even as someone who is coming from that second world of the data engineers. We probably have swung too far away gotten away from our roots in the math and the theory that really underpins why these things work. So certainly, I tend to agree we probably should fix something here. So the paper ends pretty constructively. He is really concerned with defining a new data science curriculum, taking all these thoughts and putting them together to come up with an idealized course or program in data science. So I actually compared his proposed curriculum with what you see, for example, at Berkeley's master's program in data science. And they actually pretty much overlap already, which is good. So I think both agree that exploring data and preparing it even is a first-class concern. Computing and representing and transforming data, also first-class concerns. So his first 3 points are all really software issues, engineering issues, and that's great. It really is a lot of the problem. And whereas I think both tend to focus on, yes, the modeling as an important piece, but just a piece, but also visualization. How do we communicate the results, what they mean, and how can we tell people that? And finally, correct design of experiments and doing the data science in a scientifically valid way. So I think this is good news. I think that what is passing for data science in academia these days is in the right place, or it's certainly getting closer. And it is a combination of a large chunk of software engineering and thinking about data, thinking about architecture, but also, of course, thinking about how the modeling works and how to get that piece right as well. And in closing, I'd like to also map this to what I see people do as data scientists, what maybe a lot of us in the room do as data scientists. Does it match this list of things that people say we should teach when we teach data scientists? So as Cloudera, we talk to a lot of people with lots of data who want to do data science and don't know where to start. And whenever we get involved, these are the things people are doing in their data science teams. I tried to I made a list of a bunch of customers and tried to factor out the common points, and they were these. Ingesting data at large scale in real time. Doing something in real time with the data. Serializing models, versioning models, deploying models. Making predictions on data and on engineering features at scale in real time as well. Learning at large scale over large chunks of historical data. Updating a model incrementally on the fly in real time. Monitoring it all, testing it, productionizing it, deploying it across languages, environments, and teams. So these are the actual problems I find people face in the field today. I don't know whether this is evidence that actually it is still mostly an engineering problem, or evidence that the engineering end of things needs to get its act together and get simpler. It's probably a little bit of both. I think that unfortunately a lot of what data scientists do in the field isn't the fun data science part. If you've done a course or an accelerator program, I think you get a nice big taste of all the interesting, intellectually challenging aspects of machine learning and modeling. And you go out in the real world and you don't get to do a lot of that because most of your day is stuck doing these things, which are also important. So the lesson I take from all of this is that, yes, both statistics and engineering skills are necessary. Unfortunately, a lot of the work of data scientists is engineering these days. Even though I'm an engineer, and I like to believe that data science is a lot of engineering, that's actually not a good thing. It's a problem. It's a bug, not a feature. So a lot of what I'm concerned with, what we are concerned with, what we all should be concerned with, is making these things easier, making these things more standard, making tools more standard, platforms more unified, so that these problems get easier to solve. And then we can get back to thinking about the modeling and the testing and the experimentation, and not just the engineering details. So if I had to change the world, if I had to change how we think about teaching data science and doing data science, I would focus on making the engineering simpler, standardizing the tooling, so we can get back to the fun part. So still a to-do, still a work in progress. So those are all my comments for today. I promise to keep it quick. I think we still have some time for questions or comments or objections. Start in the front here. We got a mic, yeah.
When you began, when you try to compare between computing and statistics, they began nearly the same time. But I think the problem is the limitation of a human brain to work together two tasks. So when the computer science developed, reached maturity, then they think of statistic merged with it. Because computer from the start is excellent in statistics, more than a human brain. Now, I think there is trend that we don't look at artificial intelligence as the human brain, as the peak. Now they look, for example, outside human brain, because there is intelligence everywhere. The last time, I think one of the project in making telescope for space was imitating the eyes of octopus, which it has capability, and there is a lot of field. And as long as we want the computer to limit it as we want, us will not get the enough result. Computer has better capability than a human being in statistic, especially in this field. Maybe in natural languages, there is human, because the language is a human language. So
I think you're raising a broad question here. To what extent can statistics and maybe computers model what we think of as human thought?
Yeah.
And in a way, I think you're touching on the same point that Mark Lieberman was when he was talking about the advancement of NLP. People were obsessed with imitating the human brain or invoke theories of language and not really actually doing a good job on the statistics and the prediction. Same thing in a way maybe goes for deep learning. In a way, you could say that it's a little bit precious to think that we're going to model the human brain's neurons and suddenly we'll have a brain. But funnily enough, once you scale that idea out massively and simplify it a little bit, you do get something useful. So there's probably an interesting exchange we're going to see going forward, alternating between trying to imitate humans and maybe even best what humans can do, as we really understand how we think, and therefore how computers and statistical models match or don't match that. Interesting question.
The other thing about languages, some languages, for example, you mentioned MapReduce, which is used in Java. But now Java, it has another field used, for example, in a graph database, which is using graph theory and statistic here. It is not less than, it is not easy in math. And the other thing, for example, deep learning for J. So there is capability in languages, computer languages, but just it is because it is the environment, the skill at that time, it is not enough to merge these two things. So it is issue of development.
I think sometimes engineers confuse a challenging problem, something that's hard to solve, with something that's useful to solve. So getting MapReduce to implement machine learning algorithms back in the day in Apache Hadoop, which I worked on, was difficult. And it was sort of interesting, but it wasn't actually that useful in the end. It wasn't usable for its purpose compared to what we had later in Spark. So I think maybe engineers should not get obsessed with their language and representation and focus on the problem. Sorry, I can't quite see.
Any more questions?
Hi. Oh, sure, that's a good point.
Okay. So you talked about the two different cultures, like the predictive versus the generative one. How much do you think like the data maturity level of a company has an impact on that? Because like I would assume at a company that is not really mature yet, data would be quite dirty, noisy. You would have to actually as a data scientist, you would have to dive in data, pick things together, find mistakes, and that will actually allow you to learn about what is going on in the actual like raw system. While if you are quite mature, the data would already be quite clean, and you would you don't get to the raw systems that generate the data anymore. So how do you think that impacts? How do you think data maturity impacts this kind of culture?
So I do think maturity impacts what kinds of activities are most useful. It's maybe a slightly different point than the distinction between the generative modeling and predictive modeling cultures. I think either of those could apply at an early or late stage. But in an early stage of a company where maybe you haven't thought that hard about data yet. Yes, your data house isn't in order, and it may be that very basic activities yield a lot of benefits. For example, sometimes when we engage on a project, a lot of the value just comes from the customer really looking for the first time at this data they think they have, and they realize it's inconsistent, some of it's wrong, some of it's missing, and that alone is so useful to go fix. And then, oh yeah, later, once they fix that, they can actually do the predictive modeling. So maybe in a way, you're right. A lot of the advanced modeling really, there's a prerequisite there. Having your house in order, having your data in order, and that's a big if. But in a way, that should be a more solvable problem, or ought to be an easier problem. So I think that's probably, it is true that at an early stage, you got to crawl before you can walk and before you can run. But you're still going to get value out of that as data science as well, and it's worth building towards.
Looks like nobody else has got any more questions for Sean.
Maybe one more at the front?
Oh,
Sorry, one more.
Hi. What do you think of relational databases? I mean, what's the future of them?
What's the future of a relational database?
Yeah.
I think relational databases are still certainly have their place. I mean, there are some data models that are fundamentally relational. So why not use a relational database? People maybe criticize relational databases for not scaling, but not all data problems are big data problems. Not all data are big data is big data. So as it relates to data science, in a way, data science depends on tabular data. Examples that come from the same distribution, the same form, in the same space, right? So I think relational databases being much more tied into a tabular model are still a relevant source of data. And to the extent we confuse data science with somehow being related to big data, it's almost a mistake. Big data as a synonym for unstructured, large volume data, this doesn't go together with data science. It still has to be processed in some sense and given some structure, maybe even given some relational structure in order to be useful. So although that's not my corner of the world technologically, people still obviously use relational models, and they still have a lot of value. I mean, you still implement joins today, right, in SQL. So the relational model is going to endure. One more. Sure.
A quick one. Have you got any thoughts on the need for theory in the age of big data? I mean, in kind of following what you've been saying. I mean, I don't need to know the Newton's laws because I can just get the data in.
Sorry, the need for
theory in
tiering.
Yeah, in the age of big data.
So meaning being a little more selective about what data I collect or what data I use?
No, just like say with deep learning. I mean, you have all these architectures. There isn't anything theory behind them. Pretty much, where they solve a problem. And in the same way, if I got lots of data, I can prove the Newton's laws, or I don't need to know them. I mean, that's that sort of thing. I mean, same in kind of we don't need a set of theories anymore. We just got lots of data, which gives us the answer, kind of in a very much black box type of way.
Theories, I see. So in a way, you're saying, do I need to bring my own guesses about the nature of the problem and what the right data probably is and what the right features probably are ahead of time? I guess that's lessened as with the rise of things like deep learning. The principle there is, let's just throw scale at the problem. Let's let a neural network go figure out what features are actually predictive. And I think that's good, and it does let us be a lot less selective about what features we feed in. I mean, rather than impose our own judgment informed by nothing about what features should go in, just throw as much as we can in. By the same token, I think you can, of course, that can cause subtle problems. Just because you threw data in doesn't mean it was worth doing so. If it's expensive data to collect and it doesn't improve your model much, was it worthwhile? Was it redundant with some other data you threw in? Was it data you're allowed to put in? Did you accidentally put in demographic information and your model's not allowed to know that? Or is the data actually noisy and it didn't add anything? So I don't think it obviates the need to go back and understand what your model did with that data. But it does mean we don't have to make so many a priori decisions about what data to put in at the start. We can let computers do that for us, which is great. Well, thank you very much. I'm going to be back downstairs at our booth. If you'd like to talk more about data science, Spark, Cloudera, you know where to find me. Thank you.